Hi students, under Algebra number theory, we are in Unit 2, Finite Fields and Polynomials. In lecture number 11, here we'll have a look at few theorems. Let's get on to the presentation. So before starting this presentation, I just want to give a small recap of division algorithm, which you would have studied in your third lecture. So what was division algorithm? Who had invented? Euclid, the famous mathematician, was the reason who had brought up the division algorithm. Division algorithm is just an extension of the long division of polynomials, which you have studied in your lower classes. Now the corollary of division algorithm. So what do you mean by corollary? Theorem is a main concept which is proved. Okay, from the theorem, using the theorem, we arrive at some few results. Those results will be called as corollary. So the corollary of division algorithm branches into factor and remainder theorem. So you already know what is remainder there. From the division algorithm only you know the concept of remainder, quotient, the polynomials, etc. So now I just going to state these two theorems, remainder theorem and factor theorem. So let F be a field and A belongs to capital F and F of X belongs to the collection of F of X. So you know what is a field? It should be a commutative ring. First it should be a set under a two binary operations, and it should satisfy the abelian properties and also the distributive properties. So let F be a field and A belongs to F, F of X belongs to capital F of X, then F of A is a remainder when F of X is divided by X minus A. We have seen plenty number of problems there. So F of A will be the remainder when F of X is divided by X minus A. Next is factor theorem. Let F be a field, A belongs to capital F and F of X belongs to capital F of X. Then A is the root of F of X if and only if X minus A is a factor of F of X. So these are the two corollaries what we have arrived after division algorithm. Now this theorem. If R is a ring under usual addition and multiplication, show that R of X under binary operations plus and multiplication is a ring of polynomials over R. Solution. Let me take two polynomials f of x and g of x which belongs to capital R of x. Then f of x, the sum, that is I am going to add these two polynomials and multiply these two polynomials. So addition and multiplication are also polynomials over R. This is how my declaration is. Therefore, R of x is closed with respect to addition and multiplication of polynomials, which is closed in the sense closure property is satisfied. So now I'm going to define three polynomials here. Usually you know how I define f of x and g of x, right? F of x usually been taken as a0, a1x, etc. up to am x power m. G of x is also being taken as b0, b1x, etc. And h of x is c0, c1x because it's going to be a sum of that and it's going to be a infinite series. Just observe, it's going to be infinite series. So that's why the coefficients are all the same. Just middle coefficient, for example. I'm going to take a common coefficients. Now let me prove the commutative of addition. Now I'm going to add up these two polynomials. So how will I add? Constant term, coefficients of x together, coefficient of x squared together, coefficient of x cubed together, and so on, and coefficient of xm together. Which further implies, can I write it as a0 plus b? Can I write it as b0 plus a? Yes, I can. So b0 plus a plus b1 plus a plus b2 plus a x square plus bm plus am the whole power x power m, which is equal to g of x plus f of x. So commutative of addition is proved. Next we have associative of addition. I hope you remember the associative property. Associative property will be having the same binary operation inside and outside the bracket. So you have to consider three polynomials for it or three elements. Wherever you want to prove associative, we need three elements. For closure, 2 is enough. Even for commutative, 2 is enough. For distributive and associative, we need 3 elements. So we're going to take 3 polynomials here. So what are the 2 polynomials? We just write it in the form of a summation and n plus c of that. And now can I write it as adding these two and put it up this outside? Yes, I can. So this will become f of x plus g of x plus h of x. Now we prove the identity. So identity is 0 of x, 0 plus 0x plus 0x square and so on is the identity element of R of x. Because under addition, 0 is the identity element. So far we have proved associative, commutative, and identity. So the inverse element. The inverse element of addition. So how will I write inverse elements for addition? If it's going to be negative of that number, right? So minus f of x is going to be minus a0 minus a1x minus a2x square minus a3x cube minus and so on. Why am I writing minus? So then only if I'm going to add this inverse element to that particular polynomial f of x, what will I get? I will end up with the identity element. That is what the criteria for inverse element is, the additive inverse of r of x. Now we move on to, so 4 properties of addition: commutative, identity, inverse, closure, etc. are proved. Then associativity of multiplication. Now associativity in the sense 2 elements at a time, 3 elements. So first I take 2 elements at a time. So f of x is defined as a0 plus a1x plus a2x square plus so on, and g of x taken that infinite series, just multiplying. So since already h is containing c, so I'm just replacing it by another some alphabet d, d0 plus d1x plus d2x square and so on, where di is equal to summation of all this. Now f of x dot g of x into h of x, this is the associative property, which f of x is containing d and g of x containing c, and h of x, the product will be e0 plus e1x and etc. Where en is the coefficient of x per n in f of x dot g of x dot h of x. So this is how my representation is. Similarly, we can show that the coefficient of x per n in f of g of x, that is the right hand side of the associative property. You need not to write it, you can just state it like this and it can be done. So since corresponding coefficient in these two polynomials are equal, that's the reason we can just write it as such. Now finally we come to the distributive of multiplication on addition. So we have f of x dot g of x plus h of x, which takes f of x and operate g of x and h of x, add up both, right? And you can operate the multiplicative, that is f of x over to that addition. If n is a non-negative integer, the coefficient x per n in f of x dot g of x plus h of x, that is, you know how to write it, it's an infinite series, it's going to be sum of the coefficients of f are ai, coefficient of g are b, and the coefficient of h are c. So just putting it and just operating individually, take a and b individual summation plus summation aick, and the coefficient of x per n in f of x g of x. This is f of x g of x and this is f of x h of x. So in f of x g of x plus coefficient of x per n in f of x h of x, therefore which is equal to coefficient of x per n in f of x g of x plus f of x h of x. Therefore f of x dot g of x plus f of x h of x. Just adding it. Similarly, we can prove the right distributive law for r of x. Therefore, r of x is a ring. This is how we try to prove. So first you should have the basic understanding of what is a group. What we start from set, a group, an abelian group. Then we come to ring. Then what are the distributive properties? What is a field? So much of things you have to understand before getting on to this theorem. Thanks for watching. We'll meet up in the next lecture. Thank you.